Okay, so let's dive into this. Generating electricity from the Earth's magnetic field with no moving parts, no turbines, nothing.
Yeah, just using the field itself.
It sounds, well, impossible, right? My first thought was, look, if that worked, someone would be doing it already. We wouldn't need power grids.
Right, and that skepticism is totally understandable. It comes from how we normally think about making electricity.
You mean induction? Moving a wire through a magnetic field or
Yeah.
changing the field, that whole thing.
Exactly. Faraday's law. You need that relative motion, that change. We even use induction philosophically, going from specifics to general ideas. But here,
But here, we're sitting on Earth, spinning with the magnetic field. So no relative motion, no changing field from our perspective. Seems like a dead end.
that's the standard picture, yes. But it turns out there's a slight wrinkle. Not the entire magnetic field spins perfectly with the planet.
Ah.
The main part, the dipole moment, think of it like the big bar magnet inside the Earth. It doesn't quite keep up. It wobbles slightly relative to the crust as the Earth rotates.
Wait, really? So there's a tiny bit of relative motion between us on the surface and that core field.
A very tiny amount, yes.
Okay, well then, shouldn't that generate some electricity?
Yeah.
Even a little bit. Why wouldn't it?
That's the question people like Faraday looked into like 200 years ago.
Yeah.
And the conclusion back then, using solid conductors like wires,
Yeah.
was basically no. The magnetic push on the electrons does happen, but it immediately creates this tiny opposing electric field inside the wire itself.
Like static electricity building up.
Sort of, yeah. An internal electrostatic field. And it perfectly cancels out the magnetic force, stopping any continuous current from flowing around a circuit. So everyone figured, okay, that's that. Can't be done.
So for 2 centuries, that was just accepted science.
Yeah.
Case closed.
Pretty much. It was foundational.
Until 2016, apparently. Someone decided to poke at this old idea.
Exactly. A group of physicists published a paper saying essentially, hold on a second. They argued Faraday's conclusion, the no current part, really only applied strictly to solid conductors.
Specifically, solid cylinders, like wires.
That was their key point. They modeled what might happen if you used a hollow cylinder instead, like a pipe.
And their math suggested.
That the hollow shape might, let's say, sidestep the problem. That the internal balancing field wouldn't form in quite the same way, potentially allowing a current.
Wow. Okay, that feels like a pretty bold claim. Questioning Faraday on something so basic. Was it controversial?
Oh, definitely. Yeah. I mean, you're challenging something that's been in the textbooks for generations. It caused a bit of a stir. It suggests maybe we overlooked something fundamental.
And it wasn't smooth sailing from there, I take it. Someone tried to replicate it.
Right. In 2017, another lab tried the experiment, and they found nothing. No current.
Ouch. So back to square one.
Well, not quite. The original team pushed back. They argued the replication attempt might have had flaws.
Like what?
Things like, maybe the cylinder wasn't long enough, or wasn't oriented just right relative to the Earth's field, or maybe, and this is crucial, their instruments just weren't sensitive enough to pick up a potentially really tiny effect.
Okay, so the debate continued. It wasn't settled.
No, it set the stage for a more careful experiment, which is what the original proponents then did.
So they built their own setup.
They did. A hollow cylinder, like we said, basically a pipe, about 30 centimeters long, maybe centimeter across.
And the key was making sure nothing else could be causing a reading.
Absolutely critical. They used heavy shielding against stray magnetic fields, against electrical noise. They accounted for thermoelectric effects, tiny voltages from temperature differences. They really tried to isolate just the interaction with Earth's magnetic field.
Did it work?
They reported detecting a voltage, small but steady,
How small?
around 17 microvolts, and a current of about 25 nanoamperes.
Okay, microvolts and nanoamps, definitely tiny. But was it convincing? Did it match their theory?
That was the compelling part. The direction of the current, the approximate size, it lined up pretty well with what their calculations predicted for this specific interaction with the Earth's field.
But how could they be sure it wasn't just some weird artifact of their lab?
Yeah.
Some interference they missed?
A good question. They did some clever checks. They packed up the whole experiment and repeated it in a completely different location.
It got the same result?
Got the same result. And even better, they tried changing the orientation of the cylinder relative to the magnetic field.
What happened then?
The direction of the tiny current flipped exactly as you'd expect if it was genuinely being caused by the Earth's magnetic field lines passing through it in that specific way.
Okay, yeah. That sounds pretty convincing, actually. Repeating it elsewhere, flipping the current by turning it. Those are solid checks.
It makes the claim much stronger, definitely. It suggests it's not just random noise or a local effect.
So let's talk power. 17 microvolts times 25 nanoamps. It's
Okay.
incredibly small, right?
Vanishingly small. It works out to about 4 times 10 to the minus 13 watts.
Right. So not exactly powering your toaster oven anytime soon.
Not even close. The researchers themselves are very clear on this. They call it a proof of principle. It shows the effect exists according to their results. That's the main thing for now.
So the big question then is, can you scale it up? Did they talk about that?
They mentioned it as the next step if their results get independently verified. First, replication by other labs. That's crucial.
Right.
Then, if it holds up, they say the next stage would be investigating if you could scale it for, quote, useful electrical power.
What do you think? Can you actually scale this? Does the physics allow it?
Honestly, it seems unlikely to get much power. The Earth's magnetic field just isn't very strong.
So even with a bigger pipe, you're limited by the field itself.
Exactly. You might capture a bit more magnetic flux with a larger area, but the fundamental force pushing the electrons is weak. You quickly hit a limit where the field just can't move enough charge through the resistance of a larger conductor to generate significant power.
Yeah, that makes sense. My gut feeling is you'd be lucky to get into, what, nanowatts maybe?
Yeah.
Even with a huge setup.
That seems like a reasonable guess. Probably in that ballpark, yeah. Charging anything significant would take, well, ages.
But does that mean it's useless? Even nanowatts? Could that be useful for anything?
That's the interesting angle. Maybe not for everyday power, but think about ultra-low power devices. Tiny sensors, maybe?
Like embedded sensors, things that only need a tiny sip of power.
Exactly. Imagine sensors deep inside a building monitoring structural stress, or maybe tiny environmental monitors in really remote places. Things where changing a battery is impossible or wildly impractical.
And they only need to wake up and transmit data occasionally.
Jasely. For those kinds of applications, maybe even a few nanowatts generated constantly and passively could be enough to keep them going indefinitely.
Okay, so it's not going to revolutionize the energy grid, but it could still have these really specific, maybe important niche uses. That's actually pretty cool. It's not always about the massive breakthroughs, is it?
No, sometimes these subtle, unexpected findings open up possibilities in areas you wouldn't immediately think of.
And stepping back from just the applications, the fact that this seemingly contradicts, or at least finds a loophole in, what giants like Faraday concluded, that's pretty significant in itself, isn't it?
It really is. It challenges fundamental understanding. Faraday didn't see this possibility with solid conductors. Maxwell's equations, which are incredibly successful, didn't explicitly predict this specific hollow cylinder scenario leading to a current from the Earth's field in this way.
It's like you said earlier, it makes you wonder what other assumptions are baked into our understanding. It's kind of the world's laziest power source, just sitting there.
That's one way to put it. Passively interacting with the planet's field. It's a memorable image.
It definitely makes you think.
It absolutely does. It reinforces that science is always evolving, always questioning. Even well-trodden ground can sometimes reveal surprises if you look closely enough or from a different angle.
Okay, so wrapping up this deep dive, the key takeaway seems to be this recent, rather surprising demonstration, if verified, that you can get electricity from Earth's magnetic field. But it relies on this specific setup, this hollow cylinder geometry.
Right, a configuration that seems to bypass the old limitations established by Faraday for solid wires.
But, and this is a big but, the power is incredibly tiny right now.
Minuscule. Proof of principle stage. And crucially, as the researchers themselves stress, it needs independent verification. That's the next hurdle.
Absolutely. Science relies on that replication.
That's how progress is made. Peer review, independent testing.
So it leaves us with this thought. If something seemingly so fundamental, studied by people like Faraday and Maxwell, had this little overlooked corner case, well, what else is out there? What other scientific questions that we think are completely settled might have similar unexpected twists or unconventional solutions just waiting for someone to find them? Makes you wonder about the nature of knowing anything for sure, doesn't it?
It certainly does. A good reminder that there's always more to learn, always room for surprises,